Our last speech is given by Professor Ebrahimi from Lombok University. Ebrahimi is a professor of advanced propulsion in the Department of Aeronautical and Automotive Engineering at Lombok University. His main area of research is in system dynamics and control. Currently, he is involved in powertrain design and control research-funded project working with Ford Motor Company, AVL, Cummins, Jaguar, and Land Rover. Okay, please show the video.
System modeling for powertrain virtual testing. Current models developed during the design stage to evaluate the powertrain design are not suitable for the test environment. The overall process starts by designing a physical prototype and test the powertrain either in component level, for example testing the engine or motor in the test bed, or in the subsystem level testing the whole drivetrain or the actual vehicle on a chassis dyno, and moving finally to the road testing to evaluate the design. Now, until we get to a stage that we design the final powertrain and the final product. The proposal here is to develop models that could be used in the test environment. Then these models also can be used in design stage in the virtual prototyping. Therefore, we have models that are suitable for both testing and for design and virtual prototyping. Front loading via virtual testing reduces the occurrence of late changes, and testing during the later stages of program, and it has potential to reduce vehicle prototype costs. Virtual testing utilizes models of powertrain and its subsystems and components to create the digital twin. Availability of key models is a roadblock to realization of virtual testing. Creating a standardized model library or database of models enables virtual testing. It initiates a future industry standard approach to modeling supported by component suppliers. It creates opportunity to optimize the overall design early in the development cycle. The outline of this presentation is as follows. First, we look at the overall powertrain design process. Then we look at the standard phase that the models are created in powertrain engineering. We look at the overall holistic vehicle system model, and we add all the climate subsystem to the model. Then in the next stage, we look at the test cell models, we look at the models of the dynamometers, which we use them as the virtual test beds or virtual test cells, and how is connected to the virtual model that was created in the previous section. Now, to connect them together, we need to have harnesses. Then they are basically connecting different types of models together and creating a co-simulation environment whereby we can simulate the whole process and create our virtual testing environment. And finally, we look at the digital twin concept, and we show that by creating a virtual testing environment, we are moving towards the digital twin concept in product development. Then we start by looking at the powertrain design process. If we look at the overall components that we have in a typical hybrid powertrain system, these are the components under consideration in this talk. We have our drivetrain consisting of all the connecting parts of the drive line, transmission, drive shaft, axles, and the differentials. Then if we have a hybrid system, we have a IC engine with all the components coming with the internal combustion engine, such as induction and exhaust and the fuel system. And then we have the electric drive system, which the main components are obviously the electric machines in the inverters and the batteries, and we have the control for all these modules, and we have the overall energy management system, and furthermore we have the thermal management system looking after the thermal regulation of all the components, as well as the controlling the environment inside the vehicle cabin. Then these are basically all the components that we have under consideration as to develop our hybrid powertrain. Now, in a conventional CAE-based virtual prototyping, we have once the overall system is selected, then we can start building out the models, or the first part, which is the virtual system, which consists of number of components, subsystems, which needs to be tested to get to find the parameters, model parameters, which we feed this information back into the models that are created in the earliest stage. Then we can test the overall powertrain, and once the overall powertrain is simulated and tested, we can develop the final models and validate them, which we can use these models to optimize the overall system. Then at each stage we have the feedback, taking the information to the previous stage, and as you can see that it is when we start with the models, we have minimum information about the final models, and we don't know how they can be tested. Then we have the overall model of the system. We start by component testing, engine or the electric motor testing. Then we go to the next stage. We go through the powertrain testing, and finally we can do the simulated road test on the chassis dyno, and before we go to the road test. Now, as I said earlier on, the problem here is we don't have a calibrated or validated model when we start the design, and this is a roadblock in optimizing the overall system. Now, if we take this to the overall vehicle design or powertrain design process cycle, a typical product development cycle in automotive industry, if we just look at the powertrain section, it takes something like 3 to 5 years, depending how complicated or how original the powertrain or the vehicle is. The part that we are involved with is the concept development part of the overall cycle, which takes something around the 1.5 to 2 years to develop the powertrain for the new vehicle. And if we look at the details of the concept development for the powertrain, we can see that it can be divided to two major parts. The first part is to design the design part, using computer modeling, making decision about the components that are going to be used to develop the prototype, and then with the prototype moving to the next stage of the testing until it's validated. Then during all these steps, we have the design modification. Now, until we have the final product. This is the current practice, but what we want to add to it is we want to bring the dynamic models of the powertrain in a way that we have the models of the powertrain in the early stages of design, but there are models that can be used in the test environment. Now, if we look at a typical hybrid electric vehicle model, a holistic model refers to a model that has all the components of the vehicle. What we have here, we have the overall powertrain, a hybrid powertrain, from the electric machines to IC engine, transmission, or the driveline, the battery system. Then we have the thermal management system for the high temperature cooling circuit and the low temperature coolant circuit, even including the thermal effect on the underhood of the vehicle, to air conditioning, the HVAC system in the car, and affects the variation in the cabin temperature, as well as a driver model. Then it is under input from the drive cycle. The drive cycle is a WLTP drive cycle, which is Worldwide Harmonized Light Vehicles the test procedure, which has both the variation in the vehicle speed, as you can see on the graph here, as well as the weather cycle affecting the holistic model of the vehicle. Now, how do we go in building this model? The way that we approached the problem was to develop high fidelity models, dividing it to two parts. First, looking at the deriving models for vehicle when it's active, then deriving model for vehicle when it's stationary. For the active part, we developed the models inside the Simulink software and use GT suite software from Gamma Technology to develop the thermofluid and the cabin HVAC models, and the whole powertrain was developed in a Simulink model. Then on top we have a picture showing the overall powertrain in Simulink. Then the thermofluid parts developed in a GT suite, and the HVAC and the cabin environment temperature developed in GT suite. And for the vehicle stationary, we used two different software, PowerFlow, to develop 3D buoyancy driven airflow and 3D heat transfer. And you can see the results of the two parts for the vehicle stationary. Combining all these elements creates the holistic model of the vehicle. If we go into more details for this high fidelity part, for the active part, you can see that the whole model was developed in the Simulink, which consists of all the elements of the powertrain as we saw earlier on, and the thermofluid part was developed in the GT suite, which was co-simulated with the Simulink part. Then the Simulink was the host connection to the GT, and it included all the elements of the control and the driver model and the input to the overall model, the drive cycles. Then these models created for the active part, they are all high fidelity. As you can see that they were computationally very time consuming, especially all the CFD and FEM models in the GT suite. They take a long time to run, and once these models combined, each model was validated by comparing the results of it with with a measured response of the subsystems that they were presenting. The same being carried out for the stationary part to look at the underhood model, by looking at the underhood model and the heat 3D heat flow model, we could see the effect, thermal effect of the engine, and again they were simulated and compared with the actual measured signals from the next phase was the developing models of the test cell. The test cell that we were using was a standard chassis dyno, is a hub mounted dyno. You can see that on the bottom right picture. We have the dynos connected directly to the wheel hub of the vehicle, and in case of a 4x4 vehicle, the 4 hub dynos, basically 4 electric machines that are connected by a drive shaft to the vehicle axle, that can simulate any condition that the vehicle can go through in a road. And on the top diagram you can see all the connection of the different controllers, different ECUs or the transmission control units through different CAN networks to the controller that is controlling the dyno, which is then is connected to the dyno controller. Now, having this setup, we can either test the vehicle or we can test only the drivetrain, as shown on the picture on the bottom of the screen on the left hand side. Here what we have, you can see that we have the main drive line and the differential and the 2 drive shafts connected to 2 dynos. This picture and both these pictures are courtesy of the AVL company. Again, we can see the same picture showing again the hub mounted dynamometer connected to the wheel hub of the vehicle, or on the bottom right hand side we have the connection of the drivetrain to the dynos. Then we developed the model of the dynos, having a model of a electric machine with all the dyno controller and all the control part of the dynamometer. Then we have the powertrain with a drive shaft connecting the powertrain and directly to the dynamometer. With the vehicle ECU, they are all connected to the overall controller, which is controlling both the dyno and the vehicle. Then it's generating a signal that is acting on the throttle position or the go pedal of the electric vehicle if you have electric vehicle, and it determines the required speed. And on the dyno side, the controller can determine the torque or the load applied to the shaft. And in the other diagram right on the top, we have more details of the model, which is used to build the Simulink model of the dyno. Now, once these models are put together and validated, then we can connect the vehicle model or the powertrain model to the dyno model or the dynamometer model. And the dyno model, which we refer to as virtual test cell, had a complete model of all the electromechanical parts of the system. The next part was connecting all these components together. In terms of the powertrain, how all these parts are connected together for the co-simulation, and considering they are all high fidelity models, then there were the different ways of connecting together for the co-simulation. For example, connecting the GT Suite to Simulink, and this is the part of the developing the harnesses in a way that they can we can run the simulations of the high fidelity models. Again, I'm not going to spend too much time on them. It's basically finding the best combination for setting the solvers for the co-simulation, and developing all the interfaces for the dyno, that we can have real systems showing what happens if we actually run these simulations in the test cell in a way that part of the system is real and part of the system is models. And here what we have again a drive cycle that we are exciting the overall model, which has the model of the vehicle and the model of the test cell, and taking the measurements from the virtual system. Once we have our models, the high fidelity models, now we can convert them to fast running models for real-time usage. Then they can either be used for control development on the heel rig, or they can be used for digital applications. Now, looking for the models for the real time, then we can look at the overall system or the system under the test. In our case, our powertrain. We have number of subsystems which are connected to a control unit or electronic control units. We might have number of them connected together with number of sensors and actuators. We can replicate that the same in a virtual system. Then in the digital twin we have number of models, which all together they create our Powertrain model, and we have a real-time computer which we can use it to connect to the hardware, and with this combination we can have we can create a digital twin. Now if we look at the traditional ways that conventional ways that we use the computer-aided engineering models, then we have our high-fidelity models, different subsystems as you saw earlier on. They are models, for example, in the Simulink, models in the GT suite. They can be models of the Powertrain, model of the dyno, that they run in a co-simulation environment, not on real time, and we can validate all these models by running our actual system on the test rig. Then the input to both these two environments, the virtual environment in green and the real environment in blue, is coming from the computer, which is the drive cycle. Then we put the drive cycle to a test cell and to the simulation, and what we get is the result of the simulation and results from the real system, and then we can compare them together. This is the conventional way of using the virtual prototype in the test cell environment. Now if we go to the current state of art using the digital twins, what we have here, we can substitute any of the sub-models with the subsystems in the real system. Then if we decide, for example, to replace, if we don't have the subsystem in our hardware, we can, once it is connected to the digital twin, we can replace the subsystem 2 with a sub-model 2 and run the whole system, and the hardware does the things that is running the actual hardware. And again we can look at the simulation results. Now this can be further modified by running in the test cell environment, in the physical test cell environment, or running it for a part of the drivetrain or just a component of the drivetrain, and again validate the model, which can be used for optimizing the overall system. One of the examples can be, for example, the battery models. When we don't have the batteries, we can develop battery models that are specifically designed to be used in this test cell environment, and the battery models coming from the manufacturers are not necessarily ideal to be used in the test cell environment. And using the battery model provided by the manufacturers, we can create battery models that is specifically for our test cell environment. Once we do that, we can use this battery model in other. It can reside in the library, model library, and could be used later on for designing the powertrain for a different. Then the summary of the system modeling for powertrain testing. We looked at the characterization of the components and subsystem for model parameterization and validation. Virtual testing demands quality assured models of the vehicle system, subsystem, and components. Modeling procedure for transient testing and design are presented. Testing procedure for component, subsystem, and system validation used to parameterize and validate the model. That is one of the main benefits of this approach. Experimental procedure for system identification and model parameterization are combined with the model development. Database for virtual system, subsystem components are required. This approach enables switching between the virtual and real subsystem, as we saw in the virtual in digital twin section.
Okay. Thanks a lot to Professor Ebrahimi. Hybridization of new energy vehicles is still an important direction in a foreseen future. Continue high-quality research on this topic will continue to promote economic and friendly road transportation. Thanks all presenters and participants.